All right, so welcome to Tuesday. This is the last day before the exam, so I just wanted to spend at least the first part of class asking if there are any questions about what that's going to be like as you're kind of thinking about that and preparing for that on Thursday. Yeah, Liz?
Can you, like, with radiation, like all the different equations and what does what?
Okay, so the question was for radiation, can we go over kind of some of the basics and how it works? Yeah, I think that would be fine. So I guess like we haven't covered radiation in depth yet. So maybe that's something to think about as you're going into the exam. We haven't covered it in depth. There's a reason you're not totally comfortable with it. It's obviously not going to be a major part of the exam. But I can go over at least a little bit of what I think you should maybe know at least briefly for this exam. So radiation you have kind of like two separate parts. Emitted and absorbed. And usually both of these processes are happening. Usually there's, if it's a problem with radiation, usually both emitting radiation and absorbing radiation. So emitted power is this is the emissivity. Sigma is the Boltzmann constant, and this is the surface temp. And absorbed light or absorbed radiation is usually alpha Z, which is, this is the absorptivity, right, which is like the fraction absorbed. And G is the incident radiation. So the radiation that's absorbed is always a little bit weird to handle because you don't necessarily know where that's coming from. It could be coming from a surface that's emitting light because it's at a specific temperature, or it could be coming from like the sun, which I guess technically is the same thing, but it's far away, so it's easier to treat it just as like a set amount of light that's coming in. So the G value there, that could have, that could be, I guess, something else. And so usually you're talking about like the total light that's hitting. If you have a surface like this, you know, it's emitting epsilon sigma Ts to the fourth, and light is coming in alpha G. Okay, so that's kind of the basic picture that I think you should have in your head is so epsilon sigma T to the fourth, and there's, you know, you're absorbing whatever fraction, some fraction of what's actually incident on that surface. Now, where things can get a little equation heavy is when you have like absorption and emission between two different things. So if you had, for example, you know, some surface here, we'll say it's on the ground, but we've done problems like this where we have like T sky. So now you're kind of exchanging radiation here. So this would be the surface temperature. You would be emitting from here E equals epsilon sigma Ts to the fourth. Okay, you would be emitting radiation from the sky, which is incident on your surface. The radiation that the sky is emitting, so down here, what you're absorbing is alpha G, where G is like how much absorption or how much emission the sky is giving off, how much radiation the sky is giving off. So maybe out here, G would be equal to epsilon sky sigma T sky to the fourth. And this is where things get a little bit hairy. So if you wanted to be as technically correct as possible, you could say that, okay, so you have so Q radiation equals, okay, what's the total incoming light? Would be alpha times epsilon sky sigma T sky to the fourth. That's how much heat is coming in from radiation minus epsilon sigma T surface to the fourth. Now, oftentimes our book will make a couple simplifications that make this equation a little bit more condensed than this. So often, and this is the equation that they will most commonly use. So often we assume that absorption and emission, because like physically, fundamentally, they're related processes. Often it's a reasonable assumption to assume that the absorptivity and the emissivity are about the same. That's most commonly the case. And it's also often a pretty good approximation that something like the sky, even like a wall, something like that, as long as it's a body like that, it's pretty close to a black body. So usually we say, well, let's assume that's a black body. So the thing emitting here, up here, would be a black body. So that's black body radiation, which means the emissivity is 1. Then we get Q radiation equals epsilon sigma So this is probably the equation. If you look in your book, this is the one that you'll most often see. But really, it's a kind of simplification of a little bit more complex picture. And I think, I don't know, for me, this is kind of the picture that I keep in my head. Is there's always going to be an exchange of radiation at a surface. This is the equation for what's being emitted from that surface. And then what's being absorbed at the surface is whatever happens to be hitting it times the fraction that's absorbed, the absorptivity. And then, okay, maybe I have to do some other calculations to figure out what actually is hitting the surface. you have to figure out where that's coming from. What if that's a black body radiation? Okay, I have to figure that out. If that's from some other thing, like maybe there's some extra work to figure out what's hitting the surface. But you're always looking at this kind of exchange. So what radiation is hitting the surface? Okay, we're going to get heat energy by whatever fraction of that we absorb. And then what's being emitted from the surface? Well, that's epsilon sigma T to the 4th. So you're always kind of looking at this exchange. And I think that's, for me, that's the simplest way to look at it. You can jump if you want to, like, you know, jump to a kind of simplified equation like this that takes that exchange into account. It's easier to mess up because you misidentified the situation or something like that. So like I said, for me, this is kind of this is the fundamental picture that I have in my head that I use to kind of keep signs straight and kind of think of the process. So like I said, this isn't going to be an exam on radiation, but I do think it's a good question. Because it is possible that radiation would show up in some sort of minor way. Okay. Anything else on the exam before we dive back into other stuff? Yeah, Rachel.
Well, more when the simplifying. When on a quiz we had a part with it wasn't in steady state, and like I just figured you gave us the hint that it's changing with time. Should we always assume that it's in steady state unless we're given some sort of indication like that?
So so the stuff that, I mean, the stuff that we're doing in class now, so the question is about like steady state versus non-steady state with the heat diffusion equation. The stuff that we're doing now is all the time-dependent solutions. All of the steady state solution part is stuff that's going to be covered on the exam. So if you're like figuring out a solution, that's going to be all steady state stuff for this exam. The one exception of that is if it's, there could be a question about the lumped capacitance model. So that's the one time-dependent model that could show up on this exam. But yeah, some of like the problem that was that on that quiz, the reason you weren't asked to solve that is because that solution gets very messy very quickly. So that's why we didn't actually get an analytical solution. So if you're going to have to use the heat diffusion equation to get an analytical solution, it will be something that you've seen before. So you'll have to go through the steps, but it will be something like, oh, I've done this before for the same kind of thing. Okay. All right. So where we ended last time is talking about a problem like this, where we had some solid. This was of dimensions 2L. We called that the X dimension. And we had convection happening symmetrically on either side. And this is something that if we were to look at the temperature in the thing, it's going to be somewhere at a high temperature T initial, and then it will eventually be cooling down. So it'll be doing something like that as we let time go. So starting at a high temperature and cooling down, or the exact opposite, maybe starting at a low temperature and heating up to something. And we were looking at how this can happen if we are in kind of this happy middle. So we're not we're not an object that's infinitely thin. If we're infinitely thin, then it's fairly straightforward. It heats up just like a capacitor charges up, right? It's just an exponential decay in temperature or an exponential increase in temperature. But it heats up and acts just like a capacitor, where that's storing thermal energy. It can discharge thermal energy just like a capacitor stores voltage, discharges voltage. If we are, instead of infinitely thin, if we're infinitely thick, then right far away from the surface, nothing is happening, and we see changes at the surface, and we get this kind of weird similarity solution that has the error function and these big, long, nasty things. But essentially what happens is time and space are connected, and you kind of get heat or temperature like diffusing into the surface at either short times or, again, infinitely thick, kind of two ways to think about it. When we're in this happy middle place where both time and position matter, we can still actually solve these. We found a general solution last time. We non-dimensionalized everything. We found a general solution. It was an infinite sum that looked like this. T star cosine sigma n x star, where we have kind of these two separate parts. There's like an exponential decay in time, and then this cosine term that dictates like what's happening in position, how things are changing. We had kind of two weird equations. Well, one weird one and one, I guess that's okay. So this is an infinite sum. We had this little like C term, little squiggle n. Cn, we found that from this recursive formula, BO number equals Cn tangent Cn. And we said this works, this equation works, but we have to find multiple solutions. There are, in fact, an infinite number of solutions for those little terms, C, and they happen every so often, right? Every repetition of the tangent function, we get a new solution, and then we go one period over, and that gives us a new solution. We go one period over, that gives us a new solution. So we find these between 2n minus 3 pi over 2 and 2n minus 1 pi over 2. Okay, so that would be like 0 is less than C1, which is less than, okay, so that would be 2, so that would be pi over 2 C2. This would now be 3 pi over 2 5 pi over 2, right? And that would keep repeating. So they're not going to be spaced evenly apart, and we'll see that in a second, but they're going to be about pi apart every time. And they're always going to be in that window between 0 and pi over 2, between pi over 2 and 3 pi over 2, 3 pi over 2 and 5 pi over 2, 5 pi over 2 and 7 pi over 2. So it's going to be this nice repeating pattern. That's for this equation. And then the last thing that we said is we can find this unknown constant Cn based on our C values, based on this squiggle value. And they go together. So C1 is going to go with squiggle 1. C2 is going to go with squiggle 2. C2. Call it squiggle because my C and C are, I feel like I can't pronounce them differently. So C1 and squiggle 1 go together, C2, squiggle 2. And this is 4 sine squiggle n divided by 2 Cn plus sine of two squiggle n. So we kind of have these three different equations. So this is our main equation here, but then we have these two kind of sub-equations that we need to solve and plug in values into our main equation. Okay, and we said kind of where we finished last time is we have an infinite number of terms, and we'll see in a second a little bit how this works. We have an infinite number of terms in this solution, which is a little bit of a bad thing, but as long as we're not really close to the initial condition, we don't need all of the terms. So if T star is greater than about 0.2, we really just need the first term, and that will give us a pretty good estimate of everything. So we don't necessarily need all of the terms. We can just use the first term. And if you remember from the kind of our rule of thumb for the semi-infinite solid, it was exactly the opposite. So if we wanted, we could kind of marry these two solutions. Although, I don't know, in practice, we're not actually going to do that, but you could potentially. So we'll do let's do an example problem. Okay, so let's say we are looking at heating up a chunk of tire, chunk of rubber. We know that this is 20 millimeters thick. So this is something that's done in the vulcanization process. We have this chunk of rubber. We're going to be heating it up by convection. So T infinity, we'll put it in a furnace, 200 degrees C, and convection is 200 watts per meter squared Kelvin. Okay. And the same thing's happening on this side. I won't write it again, but we'll draw a little fluffy cloud at least on both sides. We know that this is initially at 20 degrees Celsius. We know something about the thermal properties of our tire. K is 0.14 watts per meter Kelvin, and alpha is 6.35 times 10 to the minus 8 meters squared per second. Okay. So whenever we come to a problem like this, the very first thing that you should think is calculate the BO number. Because if the BO number is small, we don't have to do any of these fancy models. We can just do the lumped capacitance model, and it's an exponential thing, and it's super easy. It also gives us a sense, without having to do anything fancy, it gives us a sense of what kind of like how much the outside is going to be heated up compared to the center. Like how much of a temperature gradient are we going to expect to see? Is it going to be the outside is 200 and the center is still 20, or is it going to be about all constant? It will give us just a feel for that. How much faster is convection relative to conduction, or vice versa? So step one is calculate BO, right? BO equals H L over K, which is 200 watts per meter squared Kelvin. The length that we need, we have heat coming in from both sides, so we don't need the full 20 millimeters, we need just 10, because that's the half length. So this is 10 times 10 to the minus 3 meters divided by 0.14 watts per meter Kelvin. And when we do this, we find that the BO number is 14.3. So right away we know, okay, the BO number is pretty big. So this gives us an idea which is faster. Is it conduction in the system, or is it convection to the surface? And we can see a big BO number means that convection is fast, right? Convection is on top, H is on top, K is on the bottom. So H is big, K is little. So that means that we're going to be able to get heat to the surface pretty quickly, but it's going to take a long time to get that heat from the surface and move it all the way to the center of your rubber. So it gives us a sense already of kind of what that scale's like. If we want to look at times where the center of the tire is changing, where we can't use the semi-infinite solid. So that model is kind of by definition going to fail when the temperature in the center starts moving. So this gives us kind of like our two checks for our more basic models. Does the lumped capacitance model work? No, the BO number is too high. Does the semi-infinite solid model work? No, because kind of by definition, we're telling it that we're going to look at places where it's going to fail. We want to look at where that center is actually changing. If we wanted to look at really short times where just the edges of the tire are heating up and the center is not yet, okay, that would be semi-infinite, but we're kind of by definition not doing that. So that means we want to be looking at where center of the system is changing. It means we have to go to the exact solution. So we will look briefly at what that would look like. I'm going to turn this around so that we can a little bit at what that would be. Okay. Let me wait a second and get this back up. All right. So we need use theta star equals the sum from n equals 1 to infinity of Cn exponential minus n T star cosine Cn X star. Okay, so that's the model that we're going to use. I'm going to pull up an old spreadsheet because it's already somewhat formatted. and has a graph that's formatted. I'm just going to delete all of this stuff. Delete all of this stuff. So we're going to want, I guess, a column of X in millimeters. We'll make a column. I'll zoom this up. A column for X star. And then let's change all of these. So L, this would be 0.01 meters, 10 millimeters. Make sure I get my numbers right. Alpha, that was 6.35 times 10 to the minus 8. Our initial temperature is 25. T infinity is 200. H was 200 and K was 0.14. Okay, and instead of a time in seconds, we'll call this our T star axis. So we'll look at 0.2, 0.5, 1, 2, and 5. I'm just picking something. So this would be T of X star, and T star equals 0. And we'll call it T X star. So I'll keep most things non-dimensional, but I'll leave the temperature as the actual temperature. So we'll convert back from theta, which is our non-dimensional temperature, convert back to what the actual temperature is. So we need, okay, 0 point, I don't know. This would be in millimeters. So X star should be let's make this in millimeters then, 10 millimeters. Okay. Make this go. Oh, let's do a little bit finer spacing. All right. Okay, so X star goes from 0 to 1. Perfect. So our initial temperature is 25, but we'll hold off on kind of looking at that. It's going to be 0. Okay, so we're going to need to calculate our values for C, the little squiggle thing, and we need to calculate a value for C. We're going to do that based on the BO number. So the BO number is H times L divided by K. There's our BO number 14.3. And then we want C1 and C1. So to find this value, we're just going to estimate what it is. Like I'll call it 0.3. C1 is going to be 4 times sine of whatever that is. divided by 2 times this plus sine of 2 times this. Okay, so if C is 0.3, capital C is 1, and we could obviously change this. Okay, but we need to figure out what that actually is from this recursive equation, which is I'm gonna write it like this. I'm going to be solving this equation. So we know that the BO number equals Cn tangent Cn. So I'll use BO number minus Cn. I know that that equation should equal 0, right? Because those two sides are going to have to be the same. So I'll use that as a guess and check method, and then I'll make Excel I'll have it change the squiggle value to force that equation to be true. Does that make sense? So here, this is how I'll handle that. So I have BO number minus C 1 times tangent C1. So that equation should be equal to 0. So this is BO number minus this times tangent of that. Okay. So it's not. Yeah.
Where did you get the top this squiggle from?
I made it up.
Okay.
So I know a couple things about it though. I know one thing about it. I know it has to be, for the first one, it has to be here. So I made up a number between 0 and pi over 2, like 0 and 1.5. I picked a number. And then what we're going to do is, so we have to solve this numerically. And then what I'm going to do is say, okay, so it's not 0.3. Is it 0.4? Well, that's closer. Is it 1? Ooh, that's even closer.
Okay.
Like 1.3, 1.4, like 1.5 even. Okay, there it's actually, then it flipped sign. So it's between 1.4 and 1.5. But I'm going to do this rather than me just doing that, although it's quite fun. I'll make Excel do it. I'll have it set this to be equal to a value of 0 by changing this little squiggle value. Click solve. So if C is 1.46837, then my formula BO number minus C tan C works out. So that's the first value. I can use this same basic idea. I'll just do the first couple values. Okay, let's get, so instead of, this will be value number 2, and C2, this will be number 3, and C3 will be, just write it like this. Okay, and now I know for this one, let me get all my equations right because I didn't get that right. Okay, so now those equations are set up for all of those values. They're all the same values right now. I know the second one has to be about 3 bigger, right? Because they're all spaced out by about pi. So this is going to be, instead of 1.5, it'll be about 4.5. So you can see, okay, 4.4. Ooh, that's really close. This one's going to be about 3 bigger. So it'll be, I don't know, we'll say maybe 7.4. And then I can do the same thing. I can let solver actually figure out what that value is. So I'll set my objective here by changing this guy. Solve it. Okay, so then I'll set my objective here. Change this. Okay. So what you'll notice a couple things. Okay, so they're not spaced exactly pi over 2 apart, or they're not spaced exactly pi apart, right? This one and this one, they're actually like C1 and C2, they're a little bit less than pi spaced apart, a little bit less than 3 actually. C2 and C3, they're also a little bit less than 3 apart, but they're all about pi apart. So that's as you're starting to find like what's the next term, it's going to be about 3 bigger. But you actually have to go through, there's not a simple way to figure that out. You actually have to go through and calculate it for each step. The other thing that you can notice, like with a lot of infinite sums, right? If you add an infinite amount of positive numbers, it can often be bad. So like a lot of these sums, they'll flip sign your coefficient. So your coefficient C flips from a positive 1.2 to a negative 0.4, positive 0.2, and we would see that pattern repeating. It would flip sign every time, and it would continually get smaller. So it goes from 1 to 0.4 to 0.2. It would be less than that the next time, and less than that, and less than that. So they're always going to be decaying away, and kind of these higher order terms are going to matter less and less as we go down the line. So that's why a lot of times we can get away with just the first one, because that's the biggest one. That's the one that matters the most. It's also the one that decays away the slowest, right? Okay, so we'll see exactly how that works. So the temperature, to figure out the actual temperature, we know that this is going to be equal to, well, I'll flip it from theta to temperature. So it's going to be the T infinity plus the temperature difference. So it's going to be T infinity plus, sorry, this one minus, doing bad parentheses. And I'll lock those guys all in with dollar signs. Okay, so that is our kind of multiplication factor times, and now this is where we put in our infinite sum. So it's going to be C1 exponential, so C1 times the exponential of minus this guy squared times T, our dimensionless time, times the cosine of the times our dimensionless position. Okay, so it gets to be a little bit ugly. I'm going to put dollar signs on all of these that need them. And our time variable, position, I want to lock the column, but not the number. Time, I want to lock the number, but not the column. I think that's all good. I did it wrong. What? Oh. Okay, so that would be the first term of our system. I'm going to rescale these axes. Okay. So this is our temperature profile. I'll make these, okay, so from 0 to, from 0 to 10 millimeters, 10. Okay. So, right, the initial temperature inside the thing should be 25. And instead, this is what our model predicts, which is decidedly not 25 Celsius. And that's because this is just the first term in the infinite sum. So for this to work, we would need all of the terms in the infinite sum. And right, we lose accuracy with this as we get closer and closer to time 0. So we're going to expect, like, time 0, it's not going to work. It's never going to reproduce our initial condition unless we use all of the terms. It's kind of like, right, you can take like sine functions and replicate a square wave in electronics. But if you use just one sine function, it's kind of a garbage way to represent a square wave. If you use 3, it's a little bit better, but it's a little squiggly. If you use 50, it's a little better, but it's really squiggly. Like, it's just squiggly at the edges. It's kind of the same thing here. As we start to add more and more of these sine waves together, eventually we can get a flat line. But unless we use a lot, it's still going to be kind of ugly and squiggly. We would need to use all of them to accurately get that. So our initial condition is where this model really is pretty bad. Okay. We can add more terms. So I'm going to copy this. Make sure my parentheses are right. Okay. Need that. I think that's right. But now we need to move sort of L, B, O. That one should be L. And then our last one is in column R. So that's going to be R, R. Okay, so we have 3 terms, and now we're a little bit better, I guess. We're trying to be at 25C, a flat line. You can see we're maybe a little closer. We like average. We're now curvy around 25, but it's pretty terrible still. Again, that's because we're trying to replicate something where we would need all of the terms, and we're just using 3. As we kept adding more, we would kind of dampen out those wiggles, and it would just be a wiggly thing around 25. But initial conditions are where this model is really terrible. Oops. What went wrong? Something. Oh, this should be R. One of these things not working right. I'm wondering if I messed up my parentheses somewhere. Hmm. L. Oh. Oh, I did mess up a parenthesis. That's better. Okay. All right. That's better. So now I have this squiggle around, again, around 25C. As we start to go to longer and longer times, why is this giving me garbage? Come on, buddy. Yes, that's D. So that is decidedly not what it's supposed to look like. No, that's not right. Do I not have a minus sign there? Minus T star. It's super weird. Why is that giving me a thing that's blowing up? I'll have to mess with that a little bit. Okay. So I'll mess with this and figure out exactly why that's doing what it's doing. And I'm sure it's a parenthesis issue, but I can't see it right off the top of my head. So we'll figure that out and then figure out, I'll figure out the graph part of it. We wanted to, one of the things that we could do though, we can answer questions without doing any of those graphs. And you'll get a chance to do some of those graphs, and I'll give you this spreadsheet too. You get a chance to do some of those graphs as homework. And the last one, and kind of use that to compare, like just using one term versus using three. We're never going to use more than that because it starts to really quickly get just tedious to figure out more of these C values, and figure out like adding more terms. Your Excel spreadsheet gets like mine, and gets ugly. What we're going to do though is we could still answer like a question at, at what time does the center of the tire reach, say, like 175 Celsius. So I'm going to flip this around, because otherwise I'm going to struggle. Okay. Okay. So this, we already found C1 and C1. We just did that. I'll look up what our answers were. 1.468 and 1.267. So this is 1.468, 1.267. So the center is x equals 0. Or x star equals 0. I'm doing this at the wrong spot. Doing it above my example, I'm crashing into it. Move it down to the example. Okay. Okay, so the center is x equals 0, x star equals 0. So t equals 175 c. Theta star equals t minus t infinity over ti minus t infinity. So this would be 175c minus 200c over 25c minus 200c. So that would be, I don't know what that would be. That would be 25 over 175. So 25 over 175. That's 0.143. Right? So theta star is always going from 1, our initial condition, to 0. So we're most of the way to 0, which would be 200. We could answer a question about this because we know theta star is about equal to C1 exponential of C1 minus C1 T star cosine C1 X star. It's about equal to the first term, so we don't have to calculate all of them. So we could write 0.143 should be about equal to 1.267 exponential of minus 1.468 squared T star cosine of 0 because X star is 0. And we could pretty easily go through and solve for T star. So this would be 0.2 or 0.143 divided by 1.267 equals the exponential T star. So we would take the natural log of both sides. So T star equals the natural log of 0.14367 divided by 1.468 squared. Then to figure out the actual time, we would have to convert from this kind of goofy looking T star variable to what the actual time is. So then convert T star equals alpha T over L squared. So T would be equal to T star L squared over alpha. Okay, and I don't know what, you can figure out what that is. I have a calculator. So the natural log of 0.143 divided by 1.267 divided by squared. So this gives us a T star of 1.012. So this tells us that using just the first term was a reasonable approximation because T star is bigger than 0.2. So this tells us that this is 1.012, which is T star is a dimensionless variable. It doesn't have any units, but our other variables have units. So this would be 0.01 meters. We would square that divided by, what was alpha? 6.35 times 10 to the negative 8. 0.35 10 to the negative 8 meters per second, meters squared per second. Times 0.01 squared divided by 6.35 times 10 to the 8. So time would equal 1,594 seconds, or about almost 30 minutes. So we could take something like this and use it to figure out, okay, when does a temperature at a certain position reach something like this? We can also use it, and I'll figure out my spreadsheet, but we can use it to look at how the temperature profile changes over time, just like we have with, so we can watch a temperature at all positions as that changes over time. Although that can get a little tricky with this kind of a model at early times, especially. So I'll figure out my spreadsheet and get that working. And then I'll post that spreadsheet as part of the notes for this class. With the last 15 minutes, we're going to have kind of a, now for something completely different. So just to think a little bit about what we're doing. So we're looking at conduction. So all of these different models that we've built, all of these things that we've been handling have been specifically for conduction. And this really includes, like, from the start of class basically until now, we've been looking at conduction. What conduction really is kind of movement of particle, and like looking at how heat diffuses or moves through an object because of things like phonons, which are lattice vibrations in the object. But it's like vibrating atoms, right? And how that moves and diffuses through a solid. We have something like the heat diffusion equation, which can tell us the temperature everywhere and help us to describe that. We've done a whole bunch of different models where we've looked at these differential equations, and we've looked at the flow of heat, the heat flux. We've looked at how temperature changes with time. The fundamental physics of heat diffusion and mass diffusion, though, like fundamentally, they're kind of the same. So heat moves because of diffusion of what we call phonons, which are like vibrating atoms, lattice vibration. Mass diffusion happens, that's more easy to think of. It's like you have an individual particle moving by diffusion, like random Brownian motion. If you've ever looked at like what Brownian motion is, do you know what I mean when I say that? Like a random walk of some particle just going like randomly and diffusing and spreading out. So there's not any direction to it, but the net effect is that it moves in random ways, and eventually, that causes the heat to spread or the mass to spread out. They're governed by the same kinds of equations. If you look at like the mass diffusion equation, you're looking at concentration gradients instead of temperature gradients. So mass, you're talking about concentration. How much of it is there? With heat diffusion, we're talking about temperature. How much heat is there? That's temperature. How much mass is there? That's concentration. So they're kind of directly analogous. You can see on the right equation, the heat diffusion equation, we have a 1 over alpha. Alpha was our thermal diffusivity. It tells us how fast heat kind of spreads out in an object by diffusion. For mass diffusion, we have what we call a diffusion constant. Usually we're talking about like one thing moving in another thing, like salt diffusing in water or something like that. So you usually have, that's what the DAB means. The diffusion constant of thing A in thing B. But it's just like the same idea. It's how that material moves in some other material. Thermal diffusivity is how heat moves inside of a specific material. Diffusivity is mass diffusivity, is how one substance moves in another substance by diffusion. Okay, let's talk a little bit about solar cells, just to give you kind of an idea of the breadth of how some of these same concepts can be applied. So in a solar cell, what happens, if you've all taken chemistry, you've seen, okay, we have an atomic hydrogen, it's made up of two 1s orbitals. If we have molecular hydrogen, H2, you combine those two 1s orbitals and you get like a sigma orbital and a sigma star orbital, a bonding orbital and an anti-bonding orbital. Right, we fill from the bottom up, so you fill your 2 electrons in the bottom bonding orbital. When you absorb light, what happens is you take one of those low energy electrons and you promote it to the higher energy state. That's why if you remember in Gen Chem, you probably saw like a line spectrum of a gas. What happens is if you wait a little while, that electron in the higher energy state will fall down to the lower energy state and give off an emission. It'll give off light. That's where you see, when you've seen the line spectra from a gas, you're seeing the electron come from that high energy state and fall down to the low energy state. Okay. What happens in a solar cell is instead of like molecular hydrogen, we have semiconductors, but it's the same kind of thing. You have a low energy state that has electrons in it and a high energy state that doesn't have electrons in it. You shine light on it, the sunlight. Those electrons absorb light and go to a high energy state. Typically what happens, if you go outside and you're wearing a color, typically what happens is your electron will fall back down. Instead of giving off light like gases do in a neon light, instead of giving off light, they'll give off heat, but they'll lose energy. Your shirt heats up. The trick of a solar cell is to not let the electron fall back down, but to push it through a circuit. We push it through an external circuit and don't let it fall back down to its ground state, to the place that it was. We can do that in a number of different ways. Different solar cell technologies actually use different methods. Leaves use different methods than a solar cell. Sometimes there are some analogies in some of these systems. So basically what you're trying to do is you're trying to take that high energy electron and move it through your circuit before it gets back to the ground state. Okay, if it gets back to the ground state, okay, then you've lost it. You've lost it as heat. You didn't actually get electricity out of it. So the trick is, how do you actually separate these? One of the ways that you can do that is with a solar cell structure, something like this. This is one type of solar cell. There are lots of them actually. In this type of solar cell, we have a couple different components. The kind of dark blue, that would be what we would call the solar cell absorber, the part that's actually absorbing light. The light blue on the left, that's an optically transparent electrode. It's a piece of glass that we put something on that's conductive. So a solar cell has to have a positive and a negative, just like a battery has a positive and a negative. We have, so 2 electrodes, positive, one has to be transparent because you have to get light inside of it. That's like the whole point. So you have a piece of glass that's also that's coated with a thin electrically conductive coating. That's one electrode, your positive or your negative. And then you put your other electrode, which can just be a metal or something like that. That's the yellow line on the far right. Then in the middle, we can put a couple different materials potentially, because we have to give some sort of directionality to things. So light shines through. In your blue layer, that's where you actually get this charge, what we call charge separation, where you absorb light, you give something extra energy. Then you basically can separate it out into different materials, and that's how you kind of trick it. Instead of them coming back together, you can separate them out into 2 distinct materials and get charge separation that way. One material directs it to the positive electrode. In one material, it goes to the negative electrode. Okay, so what does this have to do with diffusion? Particles move by diffusion just like heat moves by diffusion. So if what you want to do is look at how electrons in a solar cell are actually moving inside of those materials, you can do that with the same types of diffusion equations that we've been using to look at heat. So it's like fundamentally a lot of the same types of processes. It's the same differential equations. You get a lot of the same solutions. Okay, so what we did is we looked at, we could find actually a signal. There was one of these charges, the positive charge actually absorbed light in a little bit of a different way. And we could use what's called transient absorption spectroscopy, which basically it's like a way of taking a really fast snapshot. So you can take like a snapshot at time 0, and then a snapshot a billionth of a second later, and then a snapshot a billionth of a second after that, and a snapshot a billionth of a second after that. And then you put those snapshots into basically a flipbook, right? You've all played with flipbooks. We basically take those snapshots, put them into flipbooks, and then flip it, and we can watch how charges are moving and disappearing in the material. Essentially, what we did is we took the film thickness, our absorber film, that's like the red here, and we made it different thicknesses. So if we change the thickness of our like the thickness of our thing that's experiencing heat transfer, that's going to change the BO number. It's going to basically change the relative ratio of how things are moving inside of that material versus how they're actually like getting swept away by convection at the surface. So it's like changing from a really thin thing to a really thick thing. You're going to be changing the BO number. So you're going to be changing the relative balance of diffusion inside of the object, convection at the surface of the object. We see kind of the same thing, but instead of diffusion and convection, it's diffusion of charges inside of the object and transfer from one material into another. So like transfer across the border. We could see kind of we could only see the total population of charges inside of the red material. But if we track like how fast that's decaying, how fast the basically the system is discharging electrons. We saw as we made it thicker, that rate slowed down, which makes sense. It's harder to actually start to get charges out. So what we ended up, we built this, a model like this, and we essentially had a diffusion of charges inside of the red material, inside of our solar cell absorber. On one boundary, we put a layer that charges could not go into. So that was an insulating boundary condition. So we said, okay, so the concentration with respect to X is going to be 0 at that boundary condition. That was our left-hand boundary condition. The right-hand boundary condition, if you look at that, that looks a whole lot like a convection boundary condition. That's essentially, or the right hand. So that the brown surface, that was where we could actually have charges go from the red into the brown. That's the process that we were trying to look at. And essentially we set up what is a convection boundary condition at that side. And then in the middle, we said the concentration of charges is going to vary with time. It's going to be dH dt times d, which is the equivalent of alpha. And then, okay, there was this extra term because charges could recombine and give off heat. So it got a little bit messier than just a convection boundary condition at one side. But we could figure out an exact solution for this, essentially the exact same as the exact solution that we just were looking at. It gets a little messier though because there are some extra terms, but you can see it's going to be, it's related to Bn, which is analogous to Cn. And then what we labeled as sigma n, which is analogous to like C, the little squiggle. So you get an infinite sum with the same kinds of things. You have a constant and an eigenvalue. There's an exponential term and in this case, sine term, but in our case, cosine term. So you get an exponential in one of these. Similar kinds of solutions. We could figure out, okay, we had kind of this, it got a little bit messier because the part in red is the natural recombination. It's the natural, like, electrons coming down and giving off heat. But hopefully you see some of the same kinds of solutions in there. But then what we could do is we could fit some of the data that we took, some of these snapshots, we could fit that to this model and pull out a diffusion constant and K, which is basically the convection coefficient, but convection coefficient for charges. We could then calculate a BO number, which gives us the relative size of like how important is transfer at the interface, or the convection term. How important is that relative to the diffusion term? Which one's winning? Which one's faster? Which one's slower? And that's really one of the interesting things that we pulled out is you could figure out which of these processes is the slow step. And then you can figure, okay, so if we want to design something that's faster, which process do we actually have to focus on? Do we have to focus on the interface and actually getting things across the interface, or on like the convection term? Or do we have to focus on how do we make charges move faster inside the material? We ended up finding a BO number of about 10.1. So charges moved in the materials really fast. It was actually getting them across the interface that was the slow step, or the rate limiting step. Anyway, it's 9:20. None of this is obviously on the exam, but hopefully it gives at least a little bit of a sense, like all of this, the mathematical tools and the conceptual tools can go much beyond the stuff that we're strictly covering in class to tons and tons of different fields. You can come up and pull up some of these same ideas, same equations even, in a wide variety of places. So just wanted to end on that. We'll have the exam on Thursday. So come prepared for that with note sheet and your brains, and maybe coffee because it's 8 a.m.
question.
How's it going?
Yeah, I saw it. I read your email last night, but